Okay, everyone, we'll go ahead and get started. Welcome to a talk in the Detector Virtual Workshop. Today's speaker is Professor Craig Mackay, who's a professor in imaging science at the Institute of Astronomy at University of Cambridge. Professor Mackay has had a long history of pioneering imaging devices, in particular the HST faint object camera, but also outside of astronomy in medical imaging. He founded a company, Astrocam, that's now part of Perkin-Elmer Life Sciences. He automated DNA sequencers, and protein electrophoresis systems, transmission, electron microscope, and X-ray imaging system. He also developed Lucky Imaging, and hopefully he'll talk about that today. So I give you Professor Craig Mackay. And Craig, if you could go ahead and press your talk button and get started.
Okay, can you see the my desktop now?
See it.
Is that okay? Is that visible, Don?
Yeah, I don't know. Can you hear me?
Yes, I can hear you fine.
Okay, it looks fine.
You were able to see the talk, were you?
Yeah, we were able, but now it's gone.
Okay, I'll bring it back. Can you see that now?
Yes.
Okay, that's good. Shall I get started then?
Yes, go ahead.
Okay, well, it's a great pleasure to be here today in Cambridge talking to you all over the web. What I want to do today is to tell you a bit about electron multiplying charge coupled devices and where they are going to be in astronomy. I think in some ways it's surprising that there hasn't been more impact of these devices in astronomy, but I think that part of the reason is that the whole business of trying to use these devices is very different from the way that one uses slow scan detectors, and many people are rather concerned and scared by what's involved. And really what I'd like to do today is to try and persuade you that actually there's a lot more to it and there's a lot more rewarding than that and isn't actually as hard as you might think. So what I want to do today is I'll start by giving you a general introduction to these devices and talking about their general characteristics, and then talk a bit about the applications. Why should we be bothering with electron multiplying CCDs? When are these the best devices to use? And of course, once you decide you want to use them, what's the availability of these devices like? And then the next thing is to look at just what you need to do to keep these devices happy. The care and feeding of EMCCDs, what you do, the different characteristics they have. Photon counting. They are remarkable because you can count individual photons relatively easily with them. How do you do that? How do you set up your system to give you the best results? Clock-induced charge, one of the bugbears of using these devices. What can you do to minimize it? How much are you going to get? And are you going to make any progress with it? And then finally, I'll give the conclusions. So, what are these CCDs, these electron multiplying CCDs? Well, essentially, they are standard CCDs. In addition to the standard CCD, which I show here on the picture, the top is the image area up here with the active pixels, and the bottom half is the image and store area. This is a frame transfer device as shown here. Everything in this CCD works in the perfectly normal way. The charge is transferred out to the output register here, and then is transferred around to this extended output register, and this is where things start to become interesting. In this area, one of the three serial electrodes runs not at the usual, 10 volt swing or something like that. It actually runs very much higher, maybe 40, 45 volts. And then what happens when an electron is transferred along the register into one of these electrodes, there is a very low probability, only maybe 1% or so, of giving you an avalanche multiplication. So one electron goes into that electrode and two comes out. That process continues, and of course if you have a large number of these stages, and in this particular device I've shown here, which is the E2V CCD201 device, there are 604 of those multiplication registers, multiplication pixels. So if you work out 604 to the power of 1.01 or 1.02, you get several hundred, or in the case of 1.02, several thousand gain out of this. And of course, what you have got beyond that is you've got the same old output amplifier that you've had all the time that you know and love. Running at high frequency, say tens of megahertz, you might expect that amplifier to give you many tens or 100 plus electrons readout noise, and it still does. But of course, if you now have a gain, which is very much more than that, the effective output noise is reduced by that gain factor. And so it's relatively straightforward to run the device with a gain that eliminates almost entirely the readout noise from the detector. So, what can we do about these devices? What are their general characteristics? Well, they may be read out at really quite high pixel rates. And one of the things I'll be talking about is it turns out that when you're doing photon counting, you can take liberties with these photon rates, these pixel rates. The E2V devices are spec'd up to about 20 megahertz. We run them happily at 30 megahertz, a frequency that is limited by our readout electronics and not by the CCD. And the Texas Instrument ones, which are actually no longer available, I'll come to that in a moment, these were able to run up probably up to in excess of 60 megahertz rate. The difficulty that there is with these devices is that the gain mechanism which you have on the devices is a stochastic process, and therefore there's a randomness in the gain. And that causes the signal-to-noise ratio that you get when you start with n electrons, rather than the square root of n that you would expect for the signal-to-noise, you find your signal-to-noise is actually the square root of 2n. And therefore that is equivalent to halving the detective quantum efficiency of the detector. Now it turns out that when you run them in photon counting mode, you can substantially restore this apparent loss in quantum efficiency. The other things that are going to be important are clock-induced charge, which is a generation of charge within the CCD caused by the act of reading it out. It's not a dark current which would go on to get bigger and bigger with exposure time. It is purely a per readout charge that is added on to the signal, and we'll come back and talk about that later. Next thing is to talk about the whole business of how you're going to use electron multiplying CCDs in astronomy. Well, we already had a very interesting talk by Andy Shearer on high time resolution astrophysics, and those are many of the applications that are going to be very important. What he has said in his talk was that this was a list of topics that came from the RIT High Time Resolution Astronomy workshop, which was held last year. There are many topics which are important to people working in high time resolution. A lot of the very highly magnetized stars in our own galaxy, magnetars, pulsars, and neutron stars, show very rapid variability. Black hole binary systems also are changing very rapidly. White dwarf binary systems also. And then there's a whole series of other topics such as gamma ray bursts, supernova, and then normal stars, stellar oscillations, things of that sort. And then within our own solar system, there's a lot of interest in looking at the transits of objects and trying to look at when they cover up other objects. And these can be planets and satellites. And recently there's been a very great amount of interest in objects in the Kuiper belt. These are the objects which they're like asteroids really more than anything else. They were formed when the planetary system was formed, and they're now out at very large distances in the sun, hundreds of astronomical units. We really don't know how much is there, and people are very interested to look at the Kuiper belt where it passes across, for example, a rich star cluster, to look at stars which just wink out and on again briefly, because that will have been done by a Kuiper belt object, which are otherwise quite indetectable. And so there's a lot of interest in trying to look at these things. So in astronomy, there's a lot of actual astronomical objects to look at. But of course, there are generic problems with running conventional CCDs in astronomy. If you run them fast, you tend to get a really rather high readout noise. You can easily get over 100 electrons when you run them at tens of megahertz. Most astronomy CCDs are large area ones, and they can have lots of pixels, and it's quite common to get 16 megapixel devices. And if you have to be reading these things out at less than 100 kilohertz, you find all of a sudden that in order to get this very good noise performance, which can go right down to a few electrons, you end up by wasting a very substantial amount of telescope time. And that is important given the enormous pressure on telescopes generally. If you have genuine photon counting detectors, however, there are other things that you can do. For example, if you're looking at an object that has some kind of periodicity in the signal, but intrinsically it's extremely weak, then you can run a photon counting detector fast, and you can accumulate very large numbers of these individual images and gradually bring them together in synchronization with the cycle. And that allows you to get down to very faint levels very quickly. There's another range of application which really requires a lot of speed, and these are ones where we are encountering atmospheric fluctuations of various sorts, because the atmosphere really does change in very short timescales. It can be tens of milliseconds to change significantly. And of course, if you're trying to do good work at very high resolution with very low noise sensitive detectors, you need to be able to manage all that. And so examples here are the wavefront sensors, which are used in adaptive optic systems, and these are things such as the Shack-Hartman wavefront sensor and the curvature sensor. And what they need to do is they need to be able to operate in very high frame rates, often right up into the kilohertz frame rate. So it really is quite a substantial demand on a system. And this is an example of one of the astronomical observations. It's called lucky imaging. The way it works is that we take pictures at the telescope at really quite high speed. So imagine we're working with, say, a Hubble-sized telescope, 2.5 meters. If you take a long exposure picture, then it's going to be smeared out by the atmospheric seeing, and generally you'll be pretty lucky to get 1 arc second, or maybe a little bit better than that, on a good observing site. If, however, you take these images very rapidly, what you find is that sometimes they're very sharp, that the atmosphere sorts itself out, and the image becomes very much clearer. Provided there's a star, an object in the field which is bright enough for you to recognize and to say this is a sharp image rather than this is not a sharp image, then you can use that reference star to put a quality estimate on the individual images. You can then take all the best images and you can select those, shift and add them to bring them together to give you a cumulative picture. And these are images that we took ourselves. They are, the left-hand side is an image from the Hubble Space Telescope. This is the advanced camera for surveys, which was upgraded very recently. And what you can see in there is a little group of 5 objects, the Einstein cross. This is actually 4 images of a quasar, which is a very distant quasar at a high redshift of about 1.7. The fuzzier object in the middle is a Zwicky galaxy, which is actually causing the gravitational lensing and therefore the generation of 4 images. So the picture on the left is the picture that came from the Hubble Space Telescope. The picture on the right is the one that came from our imaging system on a 2.5 meter telescope a couple of years ago on La Palma. And there you can see it's really got a very, very good image indeed. And you can see that that actually is really quite substantial. I had a talk there from Don, I think. A question from Don. No, it's gone. Can't hear. Okay, I'll just go on. So the images that you get with lucky imaging are really very, very good indeed, and you can see the high quality. One of the things that is a problem with the Hubble Space Telescope is undersampling, and you can see that in the reference star to the left. You can see the pixelation on that, I hope, on the images that you've got on your screen. And that does limit what Hubble can do. But you can see the pictures that we're getting with lucky imaging are at least as good as that. And in fact, we've recently tried to do better than that, because the concern that we have is that, okay, we can equal Hubble resolution fairly directly, but what can we do that can actually improve on that? So what we've been doing recently is putting our lucky imaging camera behind a low-order adaptive optic system to get rid of the larger scales of turbulence, which otherwise make lucky imaging completely useless on bigger telescopes. That's because the probability of you getting a sharp image goes down very rapidly with telescope diameter. So what we did is put our lucky imaging camera onto the Palomar 200-inch, that's the 5-meter telescope. They have a low-order adaptive system called Palm AO, and then we put on our electron multiplying CCD lucky camera. And the image that we got out of it was really quite remarkable. The picture on your screen now is what you'd get, what we did get on that telescope without using anything except conventional imaging. The images are actually quite good. They're about 2/3 of an arc second. The field of view is very small indeed. It's only 7 by 7 arc seconds here. But this is the picture that we got by using our lucky camera and the AO system. It's the same piece of sky, and it's almost unbelievable that it is like that. But you can see the image quality is extraordinary. And this is really a very, very great success, but it's only possible because we do have photon counting EMCCD detectors to do that. And here again you can see the comparison with the picture at the top on the left. This one here is the picture that you get without any kind of activity, just simply normal seeing on the Palomar 200-inch telescope. The one on the right is the advanced camera for surveys on the Hubble Space Telescope, and the one below it is what we get with our camera. And again, you can see this tremendous improvement in resolution in all these objects down here. So it really does produce a very substantial improvement in what you can get. Another application, which is not astronomy, of course, is for surveillance. When you start to do ground-based surveillance, you really find quite quickly that you are limited by the atmosphere. Any of you who are foolish as I am to watch shoot 'em up movies will see the chase things. This is sort of the Bourne Ultimatum type movie. You see surveillance being done at a great distance, and you think, why is the image shaking around? Why couldn't they buy a decent tripod for their system? And of course, what is actually happening is that that's the atmospheric turbulence. That's the tip tilt which dominates it. And it turns out you cannot really identify somebody, a face at a distance of even 200 meters. If you start to do high-resolution, high-speed lucky imaging for ground-based surveillance, it turns out that everything that you thought you knew about astronomy turbulence is 10 times worse. Things happen 10 times faster, and the scale over which they're correlated is 10 times smaller. And these are pictures of a screen at a distance of about 400 meters. It's got text on it, and text on it because there's something that we can recognize really rather well, and you can get a very good, accurate idea of whether it's something that you can read. These lines of text are about 35 millimeters between lines, and that corresponds to the sort of detail you need to be able to see something and to recognize somebody at 400 meters. The top picture is what you get if you just average a long exposure. And then gradually, as you take a smaller and smaller percentage, you get sharper and sharper images. There's a section of each image on the left, magnified on the right, so you can see what the image quality is like. And you can see that very quickly, as you improve the selection and ultimately do further post-processing on the data, you can get very, very high quality imaging over that distance. In the middle is a little light-emitting diode that we use for seeing characterization. But this way, by using these cameras, we're able to get an improvement in the distance. It's equivalent to bringing the target closer by a factor of somewhere between 8 and 12. So it's really quite substantial. When you're running these cameras at very high frame rate, and for ground-based surveillance, you need to be looking at several hundred hertz frame rate and very small fields of view, individual pixel sizes. Even on relatively bright light conditions, the light is really rather low, and you gain a great deal by using electron multiplying CCDs. Other applications, well, I've already mentioned surveillance for crime prevention and detection, but there are other areas where we want to be able to observe things that are moving quite rapidly and changing quickly. And in many areas of life science, the way that one does this is by tagging fluorescently labeled markers onto either DNA or different aspects of the cells, so onto neurons or other cell surface characteristics. The difficulty is that if you put an awful lot of fluorescent material on the target, you actually end up by poisoning them and or blasting them with very large amounts of ultraviolet light in order to get them to fluoresce. And that makes it very difficult to see them. And indeed, what you're measuring is actually looking at cells which are in a near-death situation. So it's very important to get that fluorescent labeling down in quantity and the light level exciting it down as well. In confocal microscopy, that is very much a problem to try and keep the light levels down. And any kind of live cell, any dynamic imaging, really needs to keep the light levels right down and the speed right up to follow what's going on. So, when should we actually be using electron multiplying CCDs? Well, this happens really any time that you're going to be limited by the readout noise. And this is much more likely to be the case when you're running at high pixel rates, because conventional CCDs give you very good read noise, but only at low readout rates. So if you're happy with a low readout rate, you're probably well advised to stick to conventional CCDs. And indeed, astronomers still consume very large quantities by acreage of these CCDs for their work, and that I think is going to continue. There have been recent developments in a variant on CMOS technology, which is generally called scientific CMOS, SCMOS technology. These devices work by having individual pixels that have individual amplifiers, which are then transferred directly to an analog chain which is on the chip. And because you can have an analog chain per column, you can get very high frame rates. 100 hertz frame rates are certainly possible, although this is best if you have a rolling shutter mode. And the readout noise you can get with these devices is really very good. You know, 1 or 2 electrons is certainly possible. The other thing, of course, you must remember if you're going to use electron multiplying CCDs, that if you do use them in analog mode, you are going to be giving up essentially half your quantum efficiency. And this can be important. But as I said, and we'll talk about more, at the lowest signal levels, you do have very much higher quantum efficiency because you can do genuine photon counting. What about the availability of these devices? Well, E2V Technologies, these company based in Chelmsford in England, these were the first company to produce electron multiplying CCDs very much at the same time as Texas Instruments. E2V called them L3 CCDs for low light level CCDs, and TI produced them as well. But they have since ceased manufacturing, and in some ways that's rather disappointing because they had certain advantages over the E2V devices, and in particular their internal amplifiers had much higher sensitivity. They were about 14 microvolts per electron versus 1.4 for the E2V ones, and that actually makes it that bit harder to run your electronics. They end up by being higher readout noise because it's equivalent to a voltage. And they also use much higher voltages, the E2V ones. They had maybe 40 or 45 volt high voltage electrodes compared to 20 volts for the Texas Instruments devices. But other aspects of the TI device were significantly less desirable in many ways. But anyway, they're no longer available, so it's not really worth spending any time on them. And what I will just run through is the availability of devices from E2V. And so there's a variety of fairly standard devices, either frame transfer or TV use ones. And these are typically 512 pixels square, right up 1024. Indeed, there's one full frame device, not a stock item, the CCD207. The main workhorses that are used are the CCD201, 1024 squared, the CCD97 at 512 squared, and there's a small device which is rather interesting, 240 pixels squared, big pixels, 24 microns. It's a frame transfer device, and it has 8 parallel outputs, and it's intended to give a 1 kilohertz frame rate. These other devices will give you perhaps 15 to 20 frames per second of the 1024 and maybe 50 to 60 of the 512 square devices. And there's a new device which also has 1024 squared, smaller pixels, 8 microns. It's a frame transfer device, faster output, it's the same physical size as the CCD97. There's also some devices in development. There's a 4K squared device, 12 micron split frame, 8 parallel outputs, giving 4 hertz frame at the rate they would normally run it at. And that's a very big device in development. And I'd like to thank E2V, and particularly Paul Jordan at E2V, for giving me all this information in good time. There's also another couple of devices which are quite interesting. There's a CCD242, which is a pinhole device. It uses a series of biased concentric ring electrodes which allow the collecting area to be changed, and it can be used for confocal microscopy. A LiDAR CCD223, which is essentially a single pixel device that runs at high frequency, and it's like a solid-state multiplier in practice, and that gives you about 650 nanoseconds sample time maximum. But generally, the devices that E2V produce are available back illuminated. In fact, that really dominates what they do. And they're available in different thicknesses, so you can get ones that are tailored for a thicker response, and that gives you an extended response into the red. But at the moment, these are specials. They're about to bring out a new anti-reflection coating, which should improve the response between 400 and 900 nanometers. So what about the operation of these devices, and also how you're going to evaluate them? Well, as I said, they're completely standard, and compared to the normal CCDs that we all know and love, with the single exception of this multiplication register, which is at the bottom of the device here. What that needs is this high voltage clock on here, or a high voltage sine wave, and the gain of the multiplication register is changed by changing the clocking, the voltage of the clocking. The scheme you need for clocking electron multiplying CCDs is shown here. You can either have a switched wave, and that's shown on the bottom of these two here, where the switch the high voltage has to reach its peak signal level before this particular phase goes from high to low. That gives you the best multiplication synchronism. and the other one is to use a sine wave, which is the top here, where you have a sine wave, again with the peak signal level on the sine wave driver is achieved before phase 1 here goes low. The difficulty when you run fast with these switch devices is that you really do have to put on an awful lot of power. If you think of a pixel time, which we're running up to 30 megahertz, so it's 33 nanoseconds pixel time, you need to get a 40-45 volt slew in a few nanoseconds. You can do that with careful design, but you end up with electronics that's hot enough to produce dinner for a family of 4 on Sunday. It really is an awful struggle. The faster you go, the harder it is to produce that. A sine wave drive can be produced really rather easily with a synchronous sort of controlled oscillator drive that produces dramatically less power and is very controllable. We find that as we go to higher frequencies, switching becomes less and less attractive, and now we've actually gone over to sine wave drivers, in fact, at all frequencies. They seem to be much easier to control. The gain that you get with an electron multiplying CCD depends very steeply on the high voltage. And this curve here shows you just how different that is. This is the high voltage here, and you can see that as you go up, you get a gain that goes up very rapidly. This is a logarithmic scale here. And what you find is that the gain roughly doubles from 1000 to 2000 in about 1/4 of a volt extra on that high voltage. And that means if you do intend to use the electron multiplying CCD at high gain, then you've got to be quite careful about the stability of that high voltage. But what we'll see is that the high gains are actually only important in photon counting mode, and the constraints there also become much more relaxed, and we'll see about this in a bit. In fact, you will not usually be running very high gain with very high signal level, and therefore the accuracy with which you need to determine the gain is not as high as you might imagine. If you have a gain of 2000, you're only going to be able to have a maximum of a few tens of electrons as you full well, and therefore measuring that with great accuracy isn't really what you're trying to do. What you find with these devices is that if you have a fixed multiplication voltage, that is, you keep your high voltage constant, then you find that the gain changes quite markedly with the temperature. And these curves here show you what happens at the warmer range. So this one here, the right-hand one, is at 293 Kelvin, that's plus 20 centigrade, 68 degrees Fahrenheit. And the inner one here is 223 Kelvin, so that's about 70 degrees change. And you can see that you're getting a drop in the voltage that you need to drive at of here something like, what's that, 1.5 volts or so, maybe a bit more than that over that range, maybe 2 volts. And what you find is that the voltage that you need, for example, to give you a gain of 1000 is 1.6 volts lower at a minus 120 centigrade than is needed at minus 60. So again, as you get colder, that high voltage that you need gets lower and lower, and that does certainly help. One aspect of electron multiplying CCDs which is important to realize, and that is that the ones that E2V make suffer from this process called aging. If you really want to destroy your CCD, you can do that quite quickly, and the best way to do it is to illuminate the image area to saturation, and then you run it at full gain, say a gain of 1000. That will cause the device to fail in only a few hours. But of course, saturation on the image area is going to be something like 70 or 80,000 electrons, and when you multiply that by 1000, you're getting 70 or 80 million electrons in the output register, and it's not surprising that you're going to do it some damage. But when you're actually using these devices, you will always be using them at very much lower illumination levels. But it does mean that if you're going to run these cameras at high gain, you have to have a mechanism which detects saturation and shuts down the high voltage if you're going to avoid any kind of damage. The sort of thing that always concerns me is leaving on a system overnight and finding that in the crack of dawn somebody has come in to clean the room and turn on all the lights flat out and done my detector no good at all. So you have to be a little bit careful that you design to take that into care. But there's no doubt that with reasonable care you can get these devices to work very happily indefinitely. And we have not had any devices that we know of that have actually died because of oversaturation. And what you actually see, the effect of it, is simply that the high voltage clock level that you need for a particular gain gradually increases as the aging effect happens. At low gains, and by that I mean gains of just a few, you don't see any aging at all. If you increase the gain from maybe 100 times to 1,000, that probably doubles the short-term aging, but has very little effect on the long-term aging. There's a short-term aging that really is concentrated in the first few dozen hours of operation. And what it is caused by is excessive signal levels in the multiplication register. Once you get an increase of 5 volts in that clock gain over the life of the device, that's about as much as you can get before failure actually happens. But as I've said, that really takes a very substantial amount of over-illumination to really cause that kind of effect. The next thing I want to really talk about is the whole business of photon counting. And photon counting is the one thing it's particularly interesting for these devices. This graph here shows you the statistical expectation, the probability of what you get out compared to what you put in for these electron multiplying CCDs. If you have a signal which is unambiguously 1 electron per pixel, then this curve is what you get, the red one here. And what you see is that the most likely gain that you get is actually unity. If you put 1 electron into the multiplication register, the most likely number you'll get out is 1 electron. Many of those electrons are going to be multiplied, but most of them are not going to be multiplied. And what you get is this turn down in the total output signal, depending on exactly what the gain happens to be for that electron as it goes down the register. These other curves show what you get out if you have increasing number of electrons, 2, 3, 4, 5, 6, etc. And you can see that it becomes a very different curve. But this probability is very important to remember because that is the thing that's going to dominate the way that you handle your photon counting. Now, what the tests I'm going to talk about are the way that we've been actually handling things, and I think we've developed some quite good and quite useful methods for managing the whole thing. The tests are all done with our own camera design, and that's now available from a company called Pixel Imaging Limited, and that's the web address if you want to go and look at it. The way that we tend to prefer to do the tests and setup is to arrange it so that there's a test chart on one side of the readout region and then have a very substantial amount of overscan. Because the really critical thing with these devices is to see what's happening in the output register separated from the image section. And what you find is that if you look at the way these devices actually, the data comes out, and this is a one-dimensional cut across an image at a very, very much lower signal level than the one shown above. And what you see is all these individual photon events. There's signal in this section, there isn't signal in this section. What you do see is a small number of events on here. What you see over here is many more events, which are due to the actual signal on the device. So by looking at this, you can separate out on the right-hand side what is happening in the image area, and by overscanning, these are pixels which are beyond anything that could have got any signal from the image area, and therefore they purely represent what's happening in the readout register, and that's what we want to look at. So, as I've said before, the additional variance that you get from the multiplication stage increases the amount of the noise that you get. If you have n electrons, that is from n photons, you'd expect the signal-to-noise ratio to be the square root of n. With an electron multiplying CCD, the signal-to-noise ratio is not what I've written here. It's not the square root of n, it's the square root of n upon 2. So what I've been saying before is actually incorrect. It's n upon 2. And that's equivalent to halving the detector quantum efficiency of the device. However, looking back at the picture we had before, you can see that if we put a threshold across here, and provided we definitely have no more than 1 photon per pixel, and in a situation where we are a very low signal level, you can be sure of that, then what you can do is use that threshold to cut across and say anything above that level is a photon, and therefore you can actually start to do proper photon counting. And by removing that variance that you get, you eliminate this reduction in the quantum efficiency. It is also important that by doing this, we're effectively removing the variance in the output signal. And of course, in photon counting mode, it also turns out that the very high gain stability that you might need in analog mode becomes very much less important, because an event is an event. It doesn't matter whether it's a big event or a small event, an event's an event. And once you've thresholded sensibly, even if you do have a bit of gain variation, then you can manage that. You've got to be a little bit careful. You can't have enormous amounts of gain variation, otherwise you will get really rather poor quality out of your images. So it's also the case when we run at high pixel rates, we can get away with some loss of performance as you might hope it to run if you're running it at low rates. And one of the examples of this is with the CCD 201. The maximum speed that E2V quote for this device depends on how you want to use it, but they say typically in the range of 13 to 20 megahertz pixel rate. All the results we've been showing here are actually using 30 megahertz pixel rate. The way you work out what the gain actually is by looking at the photon statistics. This curve on the right has got two plots on it, and these are this histogram of the event sizes taken from two separate areas. The upper graph is from one that has photons in it, genuine image photons, which are passed down in the parallel region. And the lower one is the statistics that you get from the events that you see in the overscan region. So these are entirely due to events that are created in the output register. And indeed they're created in the multiplication register largely. By looking at the slope of this curve here, which has been fitted by the straight line, you can measure directly the gain. And this can be shown quite directly from the basic theory of how this multiplication works. And indeed, the straight line characteristic shows you several things. It shows you that your theory of how it works is right, and it also shows you encouraging that your electronics is working pretty well as well. And that's always encouraging to any hardware builder. There is another component that we've got to worry about when we think about the performance of these electron multiplying CCDs, and that is the background signal. It turns out that there's two components to this dark signal. There's the thermal dark signal, and that is what's typically caused by the actual temperature of the device. And that is reduced by perhaps a factor of 10 for every 20 degrees centigrade reduction in temperature. The other one is this thing called clock-induced charge, and that is something which is effectively constant per readout. It turns out it's present in all charge-coupled devices. There's nothing special about electron multiplying ones. But the problem is that when you're using an electron multiplying CCD at high gain, these events, which you would normally never be able to see, start to become much more noticeable, and if you're not handling them properly, they can really substantially limit that sensitivity. The clock-induced charge level, which as I say is per readout, depends exponentially on the difference between the clock high levels and the substrate bias level. And this plot on the right shows you in two different modes, the inverted mode where you're actually having all the parallel clocks down at low voltage during the integration, and the non-inverted mode where one of the parallel clocks is always kept high. And what you can see here is that the clock-induced charge level that you get, and these numbers here are electrons per pixel per transfer. And remember, you will often be getting 1 million transfers to get your charge out again. So these have got to be increased quite a long way. This is 10 to the minus 4. I hope you can see it on your screen. Against this image and store clock amplitude. And what they normally would expect, that if you have full well in the image and store area, you need to have about 11.5 volts to give you reasonably good charge transfer in the device. And at that level, you do have quite significant clock-induced charge. What makes it good and what makes it bad is quite complicated. Clock-induced charge is much worse if you have low parallel transfer frequencies. If you leave your clocks high for really quite a long time, you really start to get quite increased levels of clock-induced charge. If you have sharp clock transitions, you get worse clock-induced charge. And that's almost certainly because the overshoot that you get on these transitions is what's going to cause the problems. Momentarily, you get a much higher signal, higher clock level, and that is going to exacerbate the clock-induced charge. Because remember that plot that we showed about the clock-induced charge per voltage, if you achieve that voltage, even for a very short period of time, you will worsen clock-induced charge. So it means that you've got to be very careful with the way you drive these devices. The clock waveforms have got to be properly formed, the drivers have got to be matched, and of course it's quite difficult to match these drivers through the connections that you have, particularly if the CCD is cooled, which it has to be for astronomy use. Generally, clock-induced charge appears to be relatively unaffected by temperature. We've seen some evidence that at the lowest temperature, so minus 100 centigrade and below, we do get a reduction in CIC even further, but it's not a very major effect. In photon counting operation, however, we're very lucky because there is we can change the way that we run the device. Because you're running at high gain, maybe 1 or 2,000, the image and store peak signal requirement that you have is very, very small. If you're going to have this gain and you're going to get it read out in the output register, you simply can't afford to have more than 100 electrons peak in that region. And because of that, you can use a very much smaller parallel clock swing and to transfer the charge efficiently. And what we do typically is we run with only 9.5, maybe 9.7 volts in the clock swing. It brings the surface completely out of inversion, and that gives us a very, very low level of events, maybe 1 to 1.5 events in 10 million per transfer, and that gives us less than about 0.1% clock-induced charge. As I've already said, by overscanning the detector, we can separate out what's happening in the parallel and serial parts, and we can get the clock-induced charge down to very, very low levels indeed. It's difficult for commercial cameras to do that because, not unreasonably, users expect commercial cameras to work with unity gain and high full well, and therefore they must use larger clock amplitudes, and that inevitably makes the clock-induced charge worse. But we find that if we're designing a camera for photon counting use from the beginning, we can find the parallel clock-induced charge is virtually unmeasurable. In the serial register, however, things are quite a lot harder because you still need high clock levels there, because the high gain means that you're getting close to full well, and so you're going to have fairly high clock amplitudes as well. You don't want to run with any more gain than you need to have in order not to get to too high levels in the output register. However, something that really does help you, because clock-induced charge generated in the output register, and remember, it's virtually always the multiplication register, means that on average these electrons are generated halfway along the output multiplication register, and therefore they experience a gain that is the square root of the full register gain. What you have here on the right is the picture that actually shows you these histograms from the two areas. This one is the image area, and this is from the overscan area. And what you see is that this one here, from the overscan area, is a steeper slope, indicating the lower gain that I said we should get. But more important, you can see that actually the levels here are really quite small, and this does allow you to do a lot of separation between the signal ones and the clock-induced charge ones from the output register. And of course, remember that these ones are effectively added to these ones as well. So this plot already has these added in because the output register is still part of that as well. But these also really tell you exactly how you should threshold, how you should set up the threshold for this particular operation. You can see here that if you set the threshold very high, so if you use it right up in the top end here, so you can be sure of getting essentially no clock-induced charge at all. And of course, what you're throwing away are all these events that go right up here. And remember, the most likely event is going to be unity gain. So all these ones between that curve and here are missing. And therefore, you will actually reduce the total number of events that you're actually recording with your camera. And because of that, you're effectively going to reduce the quantum efficiency again by saying quite a number of these events, which happen to be genuine photon events, are not going to be counted. However, if you set that threshold very low, you're going to get quite a lot of events which are in here, which are a combination of the tail of the noise distribution of the output amplifier and the serial clock-induced charge events. These are going to be counted in as well, and so you're going to get more contamination. So you've got this problem of trying to decide exactly how you're going to threshold devices, and that's going to really make a big difference to the way that you actually do all your work. So this is basically what you have to do in order to run these devices. It's all a very complicated business, but it doesn't appear to be too hard to do that. The electronic design is quite tricky, but only if you try to imagine that you can simply work with a slow speed design and then simply speed that up. It just doesn't work. You've really got to look at designing your camera again from scratch. But once you do that, you'll find that it really can make a very big difference, and you can get this performance really quite directly. Other problems are, of course, you end up with fairly high data output rates, and you have to have cards which are going to grab the data and let that be recorded into the computer fairly reliably. But having said that, you are able to get very substantial performance improvements with these kind of devices. So in conclusion, these electron multiplying CCDs really do offer the potential of very high performance, even at the lowest signal levels that ever. And in two-dimensional imaging systems, these really are quite unique. If you're going to design photon counting systems, with careful design and careful setup, you really can largely eliminate clock-induced charge of any sort. And if you run them in photon counting mode, you get the maximum detector quantum efficiency, and that can be get very close indeed to the theoretical amount that you should get from that device. But of course, the thresholding process always means that even if you threshold it really at a pretty low level, you are still going to lose some events. And you can work out what that is. But typically, you can get it up to about 90% or so of the official quantum efficiency that the manufacturers quote for the device. And even if you're running these devices in analog mode, the very good read noise that you can achieve will allow you to get down to very much lower signal levels than you can otherwise do. And I think it's important that these cameras can actually offer astronomers and other scientists in other research areas altogether tremendous variety of ways to carry out new kinds of research at the very, very faintest levels. So just in conclusion, I'd like to thank again Paul Jordan of E2V, who's given me a lot of information about the E2V future products as well as their current ones. Thank you all very much, and are there any questions I can answer?
Thank you, Craig. We're clapping for you. Hopefully you can hear the clapping.
Thank you very much.
Let's see, we have a few questions. I don't know if we have any questions here. There are some questions online. Let me start with online. Craig, can you see the chat window?
I can, yes, and I can see one from PM who is, I don't know who PM is. Anyway, he asks, I don't know whether everybody can read this, I'll just repeat the question. Have you tried to analyze data in a mixed mode for which some events are treated with a photon counting threshold and the brighter ones are used in analog mode? Well, actually, that is actually how we do our lucky imaging, because in order to get a significant signal from a reference star, we have to have quite a lot of photons in it, typically 100 per frame. And of course, if you're going to get 100 events in a very small area on your image, you cannot expect to photon count that, and so that's what we do. So we take the data when it comes out of the camera, have two parallel routes, one that goes through a photon counting system, and where you end up with events that are too close together, you say, actually, no, not photon counting, we'll do it analog. You have to make sure you scale these ones correctly so you calibrate the gain properly, but that works fine. And yes, it's a very good way of approaching the matter. So are there any other questions?
I just typed one, Craig.
Oh, yes.
Hold on one second.
Well, I'm not sure, Don, exactly what you mean by what instruments can we anticipate. Are there particular things that you mean we're building to use these techniques?
I was thinking.
Well, I showed you the work we're doing with combining low-order adaptive optics and lucky imaging. We've got a very nice project going with the people in Spain, the Institute for Astrofísica de Canarias. This is the organization that largely manages the telescopes on La Palma, and they also are the people who look after the GTC Gran Tucán 10.5-meter telescope, the largest telescope in the world at present. We're building together an instrument that combines adaptive optics and lucky imaging in the same way that we did it at Palomar, but with one very important change. With conventional adaptive optics using Shack-Hartman sensors, it turns out you need a very bright reference star. And that reference star is so bright that the chance of you finding one in the sky is more or less negligible, sort of 0.1% or so. And really you need to have an instrument that's a wavefront sensor that lets you work at very much lower signal levels, very, very much fainter altogether. And so what that does is forces you to look at other kinds of wavefront sensors. We've been looking at a concept design by a very interesting astronomer called Olivier Guillon, who is a Frenchman working for the Japanese Subaru telescope in Hawaii, so a nice international combination. He has got a design for curvature wavefront sensors, which, when we combine them with our photon counting devices, actually allows very great improvement in sensitivity, possibly a factor of 300. And that sort of sensitivity gain means that we can work on objects which are sort of 18.5 to 19th magnitude on big telescopes. And all of a sudden we can use this technique on almost any part of the sky, and that's very exciting. So that really does give us a big chance to improve things. And that instrument is now moving ahead. We've just recently started putting it all together, and everything is going very well.
Okay, Craig, we have a question here.
Yes, another one from PM. A follow-on question would be, what happens when there are bright stars in the field? There must be a practical dynamic range limitation. How long does the multiplication stage take to recover after reading a bright star? You lose a CCD line or possibly several lines. Well, basically what happens is if you have a very bright event, and another example that you do get is cosmic ray events, where you get in your image area maybe 1,000 electrons quite happily in a pixel or two. When you put that through the output register, yes, indeed, you just saturate it, and you can find that it takes many pixels before that actually is transferred out. So depending on the brightness of the event, you locally saturate it and you get charged smearing. And that's very much what you get in conventional CCDs. It just happens here at a lower signal level. But of course, this charge smearing really only happens in the serial output register direction, not in the parallel direction, which you normally get on slow scan CCDs.
Okay, I have a question regarding how did you define a gain using the slope on these histograms? First of all, do you have always exponential, or what we have experienced, we have double exponential and sometimes free exponential, but we built with histograms. Do you have such problem or not?
Sorry, I didn't. Your sound was rather broken up, so I didn't hear it very clearly. Do I gather that you finding more complex variations in the change of gain with voltage?
No, asking regarding how to define the gain on the CCD electron multiplying CCD camera already with aging.